Hey guys, welcome to 9.1 Basic Combinatorics. We're in chapter 9 now, where we will be dealing with discrete numbers and doing discrete math versus working with continuous numbers. That for most of the textbook, that's what we've been doing. So let's compare continuous versus discrete, just so you understand sort of what's going on this chapter or what to expect. If you talk about continuous numbers, think about an interval, let's say 0 to 10, right? And inclusive. So including 0 up to 10, you can look at this number line over here. The x-axis, you would basically say that, hey, in that interval, my x values are, 0 to 10, but it's also like not just like 1, 2, 3, 4, 5, and so forth. It's everything in between, right? It could be 4.4, 4.5, it could be 4.45, and so forth. So that's continuous. Or you can also say that's a continuum. So again, that's an interval. For discrete mathematics, it's more, hey, I have I have a set of numbers, and let's pretend this set includes numbers 1 to 10. We're not talking about numbers in between 1 and 2 or 2 and 3. It's just 1, 2, 3, all the way up to 10, like integers or like counting numbers. This allows us to, focus on patterns and sequences, and this is really useful. There's overlap between discrete mathematics and with continuous numbers, but again, we're just kind of going over some of the basics of discrete mathematics. A lot of math that you'll see in college, where if you're a math major, you will see a lot of discrete mathematics pretty early on. So it's good to kind of get your feet wet with this. In calculus, everything depends on continuous numbers, but with sequences and series, again, you'll see that sort of overlap with thinking in a continuous manner with limits, but while still having discrete numbers to work with. So let's get to example 1. So we're going to look at multiplication principle of counting, which is actually really easy. It's sort of like that scenario. You might have had that question where, hey, you have 2 shirts, different shirts, and you have 3 pairs of pants, different pants, right? And you want to see, you want to wear them to a party, and, what are the different ways you can wear it, right? How many outfits can you make? And you just do 2 times 3 and you get 6. There's 6 different ways you can wear. You can wear shirt 1 with pants 1, shirt 1 with pants 2, and so forth. And you just multiply. That's what counting principle is, right? In this blue box right over here. Pretty easy. Example 1. Some of these can be a little bit more interesting in terms of the questions. So let's do example 1. In how many different ways can 3 distinguishable objects be arranged in order? So in this case, I'm going to highlight the idea of order, and that order matters in this case. So I'm just labeling my objects A, B, C. Maybe you label it 1, 2, 3. It doesn't really matter. Okay. Now, when I write A, I'm thinking, hey, in that case, A goes first. Well, if A can go first, what can go second? Well, B can go second, or C can go second. So if that's the case, I'll do my little branch there. And so in the first spot, I can have A. In the second spot, I can have B or C, right? And I can go same thing with B. B can go first. So in that case, A and C could go second in their, little alternate universes, right? Or maybe in another universe, I had C go first, which means that maybe in another universe, then A goes second, or maybe in another universe, then I have B can go second, right? All of these are different scenarios. Each branch is its own scenario. So going back to AB, all the way on the top, I can also say, well, AB, what's the last one that's going to happen? It's going to be C, right? Well, what about AC? Well, if A then C, then that's going to be B. And then in this case, C, A, this would be B, and then A. So each branch is its own possibility, right? So you could go ABC, you could go ACB, BAC, BCA, CAB, CBA. And there you have it. Now, how do you figure out the math behind this? Because what if you had 100 things that you had to figure out how many different ways you can arrange it and the order mattered? Well, you wouldn't want to draw a tree diagram for that, but let's look at the tree branch, right? First, you had 3 elements that you started with. So in the first sort of, if you want to think about, like the first possibilities, you had 3 different things to choose from, right? Or 3 different things to pick from. Once you pick that 3, right, if you remember probability, it was replacement, no replacement. You can't pick A again if you already picked A. So, and so forth with B and C, right? You can't pick the other 2. So how many can you pick from? You can pick 2. And then after that, you can pick 1. So really, this is just 3 times 2 times 1, which is just 6. Not anything difficult, but just laying some groundwork for, for you to think about that way later on when we do factorials. Or actually, in this case, let's introduce a factorial. We also want to think about this as 3. Whoops, let's fix that. 3 factorial. The exclamation mark represents a factorial, which just means that this is the equivalent of 3 times 2 times 1.